Hey everyone, I hope you're doing well. This is a short video about the second part of the fundamental theorem of calculus. So a couple of technical definitions first, and we will use the first part of the fundamental theorem as we talk about this, by the way, so that will come up momentarily. But a few sort of preliminaries that we have to get out of the way. First, this equation right here. So if you look carefully, you will notice that what is odd about this definite integral is that the limits of integration are the same. We're integrating from a point to itself. You can think of this as there being sort of no area between underneath a single point. You don't have a two-dimensional region to have area of. Also, the delta x is going to be always 0 because there's no width to have a partition. In any event, the integral from a point to itself is 0. The other technical definition is that if you integrate backwards, right, and you will notice on that integral right there, the limits of integration, our sort of tradition is to go from a to b. This is going from b to a. And the point of this equation is that you can flip the limits of integration by introducing a minus sign. So I don't remember actually if we covered that in the previous video or not, but we'll mention it now. Okay, some less technical preliminary that is, this is an important definition. We'll say a function capital F of x is an antiderivative, so not derivative, but antiderivative for little f if the derivative of capital F is equal to little f. So this is sort of going in the opposite direction of differentiation, right? Where you are used to in Calc 1 taking a function and computing its derivative. This is trying to find a function such that when you compute its derivative, you get the original function. It's sort of going backwards from taking the derivative. And we'll see why this is important in a bit. But first of all, a natural question here now that we have this notion is, okay, if you have some function f of x, we know how to take its derivative. We have all kinds of derivative rules, and you're actually pretty good at computing derivatives. But how do we take its antiderivative? We're going to leave that question mostly aside for this section, except to point out that just by virtue of knowing how to take a derivative, you already know how to take a lot of antiderivatives. Here are some examples. If the function f of x is 3x, and I ask myself, what's a function whose derivative is 3? Well, it probably wouldn't take you long to come up with 3x, and there's not really any science to that. It's just, as I say, you have so much experience with derivatives that you can kind of sort of come up with one after a little bit of thought. What's a function whose derivative is 2x? Well, you've probably taken the derivative of x squared enough times to come up with that one as well. And this gives us an opportunity to make a point about antiderivatives. You will note that x squared plus 10 is also an antiderivative for 2x, because when you take the derivative of x squared plus 10, you get 2x. And the same is true of x squared plus 97 and x squared plus 432 and on and on and on. That is, one complexity with antiderivatives is they're not unique. One function will have not just one antiderivative, but many antiderivatives. More on that a little later. We'll just kind of file that away for now. A few more examples. The function's 3x squared. The antiderivative is x cubed, right? What's a function whose derivative is 3x squared? Again, we can come up with that just from experience. Function whose derivative is cosine would be sine, right? Derivative of sine is cosine. Function whose derivative is the exponential function is itself, right? It's its own derivative, so it's its own antiderivative. Functions that are more complicated like this, in the next section, I think we'll talk a little bit more in detail about how to compute antiderivatives for functions like this. But even this one, I bet with a little bit of tinkering, you could probably come up with the fact that this is an antiderivative. And you will notice that I kind of just took an antiderivative for each term separately and then combined them in the same way. And that turns out to be a general principle. But don't worry too much about the last one for right now. All right. So why are we even talking about antiderivatives? It's because of the second part of the fundamental theorem of calculus. And here is a statement of that, of that theorem. If my function little f is continuous on an interval ab, and capital F is an antiderivative for little f, and notice that I say any antiderivative, and that's relevant here because as we observed up above, we don't just have one antiderivative for little f, we have lots and lots and lots of them. So in this theorem, it doesn't matter which one you pick. You pick any antiderivative capital F, and then the punchline to the theorem is that you can evaluate the definite integral by just evaluating the antiderivative across the endpoints. The reason this is useful is one of the obstacles we've encountered so far is definite integrals are not easy to compute. And our method of computation to this point is to build a Riemann sum and sort of work out the summation notation and take the limit as n goes to infinity. And even for a relatively easy function f of x, that's not an easy calculation. This, on the other hand, as we'll see in some examples, is in most cases a much easier calculation. So this gives us a simpler way of calculating definite integrals. Okay, first, before we get to some examples, a word about why this is true, right? This seems to come from out of nowhere. So first, I will note that we already know an antiderivative for little f if f is a continuous function, and that's the integral up to function. That was the point of the first part of the fundamental theorem of calculus. That is, if I define a function capital F to be the integral up to x of little f, then as long as little f is a continuous function, the derivative of that function is the integrand, that is, capital F prime equals little f, which is the same thing as saying capital F is an antiderivative for little f. Okay, so I'm also going to note that if capital G is another antiderivative for little f, right? So capital F is the integral up to function. That's automatically an antiderivative by the first part of the fundamental theorem of calculus. If capital G is another one, and I know again that functions can have lots of different antiderivatives, so there's nothing sort of strange about that. Well, then the functions capital F and capital G have the same derivative. They both have little f as their derivative. And so that means they differ by a constant. You should check out the notes and exercises, by the way, for a sort of longer discussion of why this theorem is true, which breaks this down into smaller steps. So if this seems like it's a little bit dense theoretically, check out the notes and exercises where this is expanded on a little bit. Okay, in any event, if f of x and g of x differ by a constant, all I have to do now is note that when I plug an a into capital F, right, so here's the input variable in capital F, it's the upper limit of integration, so capital F of a would be the integral from a to a. And as we said above, that's equal to 0, right? You integrate from a point to itself, you get 0. And that means in this equation, if capital F of a is 0, then capital G of a must be equal to negative c, or c must be equal to negative g of a, doing a little bit of algebra. Similarly, capital F of b, so I'm just taking this definition for capital F and plugging in a couple of different inputs. First, I plug in an a for x, then I plug in a b for x. When I plug in a b for x, I get the thing I want to compute, right? The integral from a to b. And what should that be? It should be capital G of b plus c. But c is minus g of a, so I get g of b minus g of a. And what is the conclusion? G here was any old antiderivative of little f, and I've concluded that the integral from a to b of little f is capital G evaluated across the endpoints, which is what we wanted to show. Okay, a few examples of how to use this, and this is something that you'll find yourself doing a lot more than worrying about the theory. Suppose I want to compute the integral from 1 to 4 of 3 dx. Now this is not a hard integral to do anyway, because the 3 is a constant function, so its graph is a horizontal line. So this amounts to the area under the constant function 3 over the interval from 1 to 4. That's the area of a 3 by 3 rectangle, or 3 by 3 square, I guess, which is 9. And you can see the answer comes out to 9. But if we do this using our new strategy here, our new strategy is find an antiderivative for the integrand. Well, what's an antiderivative for 3? Well, I picked one of the functions from our table. We know that 3x is an antiderivative for 3. And then what do I want to do? I want to take that antiderivative and kind of do this, right? F of b minus f of a. So there's two sort of steps that I have to take. First, I have to find the antiderivative. Then I have to evaluate across the endpoints. To slow that down a little bit so that we don't have to do everything all in one step, we'll introduce the notion of an evaluation bar, which is right there. And what this evaluation bar means when I put it to the right of something is take the thing to the left, plug in the top number, and subtract what you get when you plug in the bottom number. That is, evaluate across those endpoints. So my first thought here is, what's an antiderivative for 3? It's 3x. Okay, so I want to take my antiderivative 3x and evaluate across the endpoints. And then in the next step, I can do the evaluation, right? So I plug in a 4, and I get 3 times 4. And I subtract what I get when I plug in a 1, 3 times 1, and it comes out to be 9, as predicted. So this basic methodology, because of the second part of the fundamental theorem, this will work anytime I can figure out the antiderivative of that integrand. So here's another example, right? What about the integral from -3 to 4 of 2x? Again, this is another one that you could do using geometry, but it's actually a little easier, I think, using the second part of the fundamental theorem. Antiderivative for 2x, well, I can use any one I want, so I'll pick the simplest one, x squared. And then I evaluate x squared across the endpoints, which are -3 to 4 in this case. Do the evaluation, right? 4 squared minus -3 squared. And that comes out to 16 plus 9, which is 25. Wait a minute here. I didn't do that right. 4 squared, so let's fix this. 4 squared is 16 minus -3 squared is -9, and that comes out to be 7, right? Okay, so there was a little error there that we've now fixed. Couple more examples. One that is a little more substantial. Here's an example that would be definitely a little bit difficult to do using Riemann sums, not impossible, but nonetheless. To do this definite integral using the second part of the fundamental theorem, I want an antiderivative for 3x squared. That is, I want a function whose derivative is 3x squared. Well, x cubed, of course, is a good choice. The derivative of, x cubed is 3x squared. And I need to evaluate across the endpoints. Okay, so when I plug in a 10, I get 1,000, I plug in a 0, I get 0, and there's my answer. And you can see that this is a pretty quick calculation. This is not a lot of heavy lifting to do this calculation. So that's definitely an improvement on Riemann sums. And then I'll just do this last one here. Admittedly, the one in the last row may have been a little tricky how we came up with the antiderivative, but the point is that once we have an antiderivative, even a kind of complicated looking integral like this is not that hard, right? If I know an antiderivative for the integrand, then I just evaluate it across the endpoints. So here's my antiderivative from up above. I evaluate from 2 to 0, and it's just sort of plug and chug from there, right? You plug a 2 into the antiderivative, that gives you that thing, and you subtract what you get when you plug a 0 in, you do some math, and this comes out to be the answer in the end. Okay, so that's the second part of the fundamental theorem. Let me say a couple things in conclusion and then encourage you to go practice the exercises. We have 3 sort of ways of interpreting or understanding a definite integral at this point, right? So when we see this symbolism, I think 3 different thoughts kind of swirl in our mind. The first is the geometric interpretation, right? We built this thing to compute area. And once we built it, we realized that what we were actually computing was net area between the graph of the function and the x-axis. So try not to lose sight of this. When you're computing definite integrals, you're always computing net areas. The second sort of understanding of the definite integral is it's the limit of approximating Riemann sums. Now, it's tempting, given these calculations, which are so much easier than Riemann sum calculations, to say, why don't we just throw those out at this point? Why would you ever want to do an integral like this using a Riemann sum? And the answer, of course, is that you wouldn't. That integral is much easier to do the way it's done on the screen now. However, finding antiderivatives is an imperfect science, and there are lots of functions for which antiderivatives are just not available. And so the second part of the fundamental theorem won't work. There are also a lot of applications in which it's not clear what the right integral is to calculate in order to compute what we want to compute. And so we'll use Riemann sum approximations to guide us in those cases as well. And we now have a third understanding of definite integrals. That is, if I know an antiderivative for this integrand, then this is not that hard a computation. All I have to do is evaluate the antiderivative across the endpoints. Okay, that's good for the second part of the fundamental theorem of calculus. Be well, take care of yourselves.